Hello and welcome to the newest FLUXANA seminar. I will be your host today. My name is Konstantin Brendkens, and today's topic, as you can see on the screen, will be one of our application examples. And the material or the application we will be talking about today is continuous casting powders. Before we get into it, I would like to address a thing that we saw on one of our last webinars. You can always enter or enter question in the Q&A section of this webinar. On one of the latest webinars, we had a lot of questions that were entered into this question and answer section as anonymous. It's a checkbox somewhere, and the problem we have with that is we cannot answer because we do not have any email connected to a questions that is posed anonymous. So if you want to make sure that you get an answer to your actual question, you can either just uncheck that box when you're answering it. We are the only ones seeing the question, so it should be fine data protection wise. There is also the option to just enter an email address there that we can answer to, or to simply write the question to info@fluxana.com. We will see that email address in one of the later sheets where the announcement for the next webinar is. So just to make sure that we can get back to you with inputs and answers to your questions, make sure that you don't post them anonymous, because that does not allow us to answer you. All right, having that out of the way, let's get started with today's topic. As already mentioned, we'll be talking about one of the applications, or in this case, multiple ones that we run here at FLUXANA Laboratory. And the material we'll be talking about is continuous casting powder. So let's start with the obvious question. What is continuous casting powders? What are these? Where is it used? And this is a very specific one. Generally speaking, wherever you have liquid metals touching basically or getting in contact with oxygen, there is a need for protection here to avoid oxidation and other effects. So wherever you have this, be it either on the top of a pan with a liquid metal, or also in like a continuous casting plant here where you just make these metal sheets basically, or if you are casting in some sort of dish, there is always a powder used to protect the metal basically. So when you have liquid metal and you want to protect it, that's where you use casting powders or continuous casting powders. And there is a very nice definition on the German Wikipedia. Unfortunately, I did not find any English translation. So we made this little summary here for you. So basically, casting powders are slag formers, and they are used as a lubricant and also a release agent when you want to do any sort of metal casting. And the way it works is that the casting powder is added on top of the molten metal, and it then forms the slag. In combination with the hot liquid metal, it forms the slag, and that protects the metal beneath, and it also helps with thermal isolation, lubrication, and works as a release agent. And during the solidification of the metal, then the cooling down and getting solid, it also absorbs the non-metallic inclusions, and they all end up in the slag on the outside. And yeah, that's where we use the continuous casting powders. Here in FLUXANA, we have two applications connected to them. Well, in truth, it's a bit more, but it's basically two groups. The first one is the FLXCC raw, which analyzes the raw materials that are used to make the casting powder. And the other one, FLXCC, is for the analysis of the casting powder itself, of the mixture here. And one of the interesting analytes in these applications is fluorine. So what we found in our communication with customers from different industries is that a lot of the knowledge and well, a lot of the tricks we use here for these samples can also be applied to other materials like welding powders, for example, or even welding electrodes, because chemically they are quite similar, basically. So we'll be, in generally, we'll be talking about those two applications today, the FLX raw and the FLXCC. And let's go into the details of the samples first. You're probably familiar by now with the way these webinars for the applications are set up. So we'll talk a bit about the samples. And when it comes to the continuous casting powder, again, we have a definition here that I didn't find a translation for. So I did the translation myself, basically. So the continuous casting powder is usually just a mixture of alumina, limestone or lime, carbon, quartz or silica oxide, and fluorescent or, well, calcium fluorine. And these materials are mixed in powder form. In very rare cases are they kind of melted together, but usually those are mixed on site where they are used from these raw materials, from these raw powders. And that ends up with an application like this. This is the general composition or the concentration range of our FLXCC. And yeah, we as a special feature, we can already see it's high fluorine. Well, we start at 0, but we go up to around about 10%. And another interesting thing is that we also have carbon in the sample, both as carbon elemental and CO2, so a mixture. Just a quick reference here to one of the FLUXANA CRM sets, a bit of advertising, if you will. Recently, there's this set basically, which are actual casting powders taken from from our customers, and we put them through certification. So you can get those as a set now, which greatly helps with reference samples. But let's get back to the material in general. So the sample, as I said, we have this range of concentration, and we have the special well, the special elements, fluorine and carbon, to worry about. So what is there to worry? Well, after sample, we usually talk about the preparation. So let's get into that here. The preparation of choice here is fusion. Why we'll come to in a minute. But basically, yeah, we mix the sample with tetraborate. This mixture goes into our platinum. Then we do the fusion, and we have a fused bead in the end. And we've done this with a gas machine in the past, and we switched to electrical recently. More on that later. Application-wise, as I mentioned before, we have the CC raw and the CC. There is not much to talk about CC raw. This is your typical general oxide raw material program. So I think we covered that in the past in one of the other episodes. Is basically you take your sample, you calcinate it, or you ignite it, and then you mix it with the tetraborate and do fusion, and you have a general program from 0 to 100% of various oxides, alumina, silica, calcium, you name it. So the CC raw is kind of boring. The more interesting application is the actual casting powders. And the first problem we have here in preparation is the high content of carbon. You've seen before that it's up to 20% in total. And when it comes to doing a fused bead, what we want is something like this, a clear disc, completely homogeneous. But the problem is if there is a lot of carbon in your sample, this tends to not dissolve well. And also, well, it stays in the sample if we can't get it out. So what we end up with is the examples on the right here. We can clearly see that there are particles as well as bubbles inside our fused bead. And this is basically the same sample where this one was calcinated before and this one was not. So this one was done directly, although I think this one is a different sample, but these one and this one are the same, but with different pretreatments. So the problem we have is if our sample contains a lot of carbon, we need to get rid of that before fusion. If we are using the gas machine that is now, we'll kind of split it here. Historically, as I said, we have been doing this preparation with the gas fusion machine. And the problem here is that our burners or the heating source is directional. We have the burner going basically up like a Bunsen burner, and then we have the crucible on top. And what that means is that the carbon does not get burned away efficiently. So if you have a lot of carbon, your standard program will not be enough time to get rid of it, and you end up with a fused bead like this, where we still have undissolved carbon that we then cast into our dish and it forms out. It's fine for the platinum ware, but for the dishes it is not. So the solution here, again, I did not bother to translate this. This is our German instruction on how to do this. The solution for this is to simply burn away the carbon before we do the fusion. So what we end up with is a calcination step in a muffle furnace. I think it says here, like we do it like 10 minutes or something at 700 degrees. Yeah, it says here 10 minutes, 700 degrees. That's how we get rid of the carbon, and then we proceed with the fusion afterwards. So this is how we used to do it a while ago. It is fine for samples with a little carbon. Let's say like below 5%, that works fine doing it directly. But if you have more than 5% carbon, you definitely want to do the pre-treatment before. One of the big advantages of the more modern electrical fusions is that they are basically muffle furnaces. So we can combine the two steps. And what we do here is we don't need the pre-treatment. We do a different trick while usually we would mix the sample with our tetraborate. Here in this case, when we know it's a lot of carbon inside, we simply put it on top and then start the fusion. So what happens is it can burn away in the fusion machine, in the muffle furnace, before it starts getting liquids and before the agitation and whatnot starts. So this is a more convenient way to get rid of the carbon, and you can simply run it in one machine without having to use two, like for example, before in the gas machine, where we would do the muffle furnace first and then the actual fusion after. So that works fine. The next special thing we need to look out for is fluorine. Fluorine as an analyte is quite difficult in XRF analysis, just mainly because it's a very light element. You might remember, you might have seen a table like this before. We definitely use that one in a lot of our other presentation when we talk about the theory and the general the general way to analyze certain elements in X-ray. I think I've heard the name in English is what they call the critical depths of analysis. We call it like saturation depth. It's basically, if you look at an elemental line and a fluorescence line, the question is, how far do we look into the sample? What depth of the sample does our fluorescence come from that we analyze? And when it comes to fluorine, we have to be aware that it's absolutely surface analysis. Like the FK alpha, even in a graphite matrix, is only 5 micrometers in saturation depth or critical depths. And as your matrix gets heavier, like silica or iron, it gets even worse. So we are only really looking at the surface. So that makes it difficult to get reliable concentration analysis. And it also explains why, especially for fluorine, our casting dishes need to be like in peak condition. You know that the platinum deforms over time, so it has to be recycled regularly, depending on how much fusions you do. And in our laboratory, we kind of stuck to the habit nowadays that we have an extra set of dishes for fluorine analysis. So if we know a sample is coming in and somebody wants us to quantify the fluorine, we use the special dishes. I think we have 2 of them, and usually we do like a cleaning run, and then afterwards we use the special diff, because we know that the shape is very important here because of what I said earlier. The analysis really only happens in the first few layers of atoms, basically. So that is something to keep in mind. Also, something we found out, we know, is that the fluorine is highly volatile. So we have to make sure that the fusion is always done at the same temperature. And this is difficult with gas machines. So we have been doing the fluorine with our gas fusion machine, as I mentioned before, but only with limited success. What we have with the modern version of these machines, where we have a muffle furnace, is we have a way more accurate way of controlling the temperature, and that helps us a lot here with the reproducibility. So to make a little explanation without going into too much of depth here, if we look at the fusion cycle, we have our target temperature, and then what we have is an autosampler that loads the sample. And of course, when he loads the sample, we lose a bit of temperature. And then it is heating up again. And then for the cycle of the fusion, it is stable. And then the whole thing starts from the beginning. So what happens is that we need to make sure that this target temperature is always the best like the best accuracy we can get. And in terms of our machine, what does that entail? First of all, it means you need to give the machine enough time after startup to heat up. Usually our machines start up from like from room temperature to fusion temperature in about 60 minutes. I would recommend even giving like maybe half an hour longer to get stable. And then the critical part now is, if you run a series of samples, one preparation after the other, you have to make sure that the machine has enough time in between those samples to get to a stable temperature again. Because each time you load and unload, the temperature will drop, the machine will react by doing more heating, and you will end up with like a sort of, like these little squirrely lines. And what we find out is that usually we give it like 1 minute of stabilization time in between samples. So this is loading, this is unloading, and this is loading of the next sample. Between those, we give it 1 minute. With fluorine samples, with the fluoride samples, we opt to actually give him some more time. So in our machines, we can give, it's called, I think, fusion stabilization, and we can give it a time frame, and usually we do like 2 or 3 minutes, just to make sure that every fusion we do is done at the same temperature profile and the same time, so that we get a good reproducibility in the end. Otherwise, if you do it so fast, what tends to happen is that if you run a series of, like, let's say 10 samples of the same material, you will see that the fluorine value will gradually drop. The first one will have the highest, and the last one will have the lowest, and you will have like a continuous degrading of the fluorine value. So you have to have some sort of compare that, and yeah, we kind of fix that by giving it little breaks between the sample preparation, basically. Yeah, our beautiful machines in all their glory. I think you've seen them before, so let's just go over that. Next up, the analytical program. We always get a lot of question about how do we run that on the spectrometer. It depends a lot on the spectrometer that you have in your laboratory, of course, but let's go over a few of the details. First of all, as I think I mentioned that already, like the first method, the first time we made like we make a continuous casting powder method was on the gas machine back in the day. The electrical ones were not really present in the market. They were not like available, let's say. So we developed it on a gas machine, and especially the calibration for fluorine was purely synthetics. We basically used CAF2 and a few samples to mix our calibration. So it was kind of artificial, if you want to call it. And we used other materials, different materials, to fill the gaps. This is old news. So in the meantime, a good thing that happens is a lot of certified reference materials became available. Not only the FLUXANA set that we had in one of the sheets before, but also other ones. So what happens is that the old set that contained like 30 samples, it became a lot smaller, and using CRMs make it a lot easier and more more readily available. So the new set we'll talk about in a minute. An interesting thing that comes from the carbon problem we talked about before, or basically it comes from the carbon mass missing in your final fuse speed, is that if you look at the system and you look at the sum of standards, it's probably too small to read here, but we have a larger table later, is the sum of all your standard materials, the analytes, is not 100%. And that is basically because in fusion, we lose sample mass. We use carbon, for example, and we have to make sure that our calibration takes that into account, because as you can see from the table here, if we assume that we have 3 samples, the first one having 0 LOI, the second one 5, and then 10%, and we always do the same ratio of sample to flux, the final fused beads ratios will be like wildly different, because this one will lose 5%, this one will lose 10% in fusion preparation. So the ratios of sample to flux will vary. And in FLUXANA strategy, this is not a good thing. We like to keep the ratio as stable as possible, so that we have that makes the calibration more easy. Usually softwares can compensate, but we don't like doing that. We like to have all of our standards basically doing the same. And in this case, we need to make the calibration in a way that this is represented. So let's come to the more, like, this is the last or the most recent version of the CC that we are running on our actual this is the one that we are using now. So this is electrical fusion. And as you can see, the standard set is much more compact, and it actually consists of different types of samples. The first ones here are unannealed or unignited samples. So it's samples as is, and we lose the LOI during fusion process. So it's all original samples, and the ratio varies a bit. Then we have a few selected additional samples that are annealed or ignited before. So here the LOI is 0. We take 1 gram of ignited sample and we combine these. That's a double one. We combine these into a set, so that makes us able to actually have the LOI as a part of the analytical system. And that even allows us later to report LOI for unknown samples. If you look at the sum of these analytes, you can see there are some funny numbers here. mostly this one, which is 100% in some, which is quite a lot, but that's because this is basically pure calcium fluoride, and we report CaO, or we report calcium as calcium oxide. So that adds a bit of oxygen to the mass, and that's just a mathematical thing. But yeah, the key part is that we take the LOI as part of our sample, and that also allows us that when we run unknowns later, we can calculate the LOI as a rest to 100, basically. A few details about our programs. People always like seeing how does FLUXANA do certain things. So this is the actual program in terms of the analytical lines that we are using. And I think we picked a few examples here. So that's calcium. I think this one is a bit more interesting, as I talked about fluorine all the time now. You can already see from the counting time that we are kind of empathizing on this, like we're putting more spotlight on the fluorine here, while the other elements are only run for 10 seconds. And then we have like magnesium and sodium a bit longer. So it's kind of, yeah, the typical one. Yeah, I think one of the good achievements that we have, if we remember before, the gas version had like 0.8 as a standard deviation, and we are down to 0.4, which is quite an improvement, I think. And then, yeah, we have silica as another example. Not much to say here. It's just like a standard calibration range, so to say. Results formats or result report. We've got the specification here. So if you want a sample analyzed, that's what we can do. One interesting thing again to point out is we always have these limits of detections that we kind of calculate for our method. So each individual method that we are running in the laboratory will have some sort of this, and you can see that fluorine is like exceptionally high. Basically, that we explain this by yeah, what I said before is the analysis is only at the very surface of your sample, and you also have this volatile effect during preparation. So the limit of detection is yeah, not as good as you would expect. So it's in the end, you can't really report anything below 1.1% with XRF. And I think I actually skipped an important point here. I might come back later, but yeah, pressed pellet as a different preparation method where you don't dilute and you don't do the high temperature step is even less of an option, because you even have more fluctuation in your preparation repeats due to like the particle effects and whatnot. So fusion is basically the only way to do it, but we have the problem that we cannot detect low concentration of fluorine well here. The way we do it is here. I think I'd actually like to skip over this because time is getting short. There are other webinars available and coming which will deal with this more statistical side of our analysis. So this is one of the sheets that explains how do we get our limits of detections. As quickly speaking, is we do 10 blanks, and it's 9 times the standard deviation. So basically just the area of trust around this to see how can we be sure that this is not zero. But there is other webinars, as I said. And yeah, a few data from a bit of more data from our settings. So what you do at the end of a calibration, I think this should be clear to anyone by now, is that like you do a validation, of course. So this is actually our control sample in our control chart, but basically part of the set we have 2 CRMs, the 124 and the 176. And what we check first is for correctness. This is our test here from our tables. I basically just took this out of our documents. So that is what we call the correctness test. We check target value versus the CRM certificate and its area of trust. And then for long time control, we make regular preparations of these samples. And yeah, we run them versus our areas of trust. And then, well, this is actually this here. We have regular samples, and then we have like a warning and an action threshold. And yeah, just wanted to show for the same elements we talked about before, we have the data here. And then, yeah, that's about it. So in summary, for the applications, we have basically two here. We have the raw materials and the mixture of powders that we want to control for our casting powders. As mentioned, not so in depth, but generally speaking, fusion is the good way to do preparation here. And the electrical fusion has some advantages over the gas fusion system. Although you can still do it with gas fusion, but don't expect like miracles on your fluorine values. So just, get in touch with us if you want some details. Of course, the standard should be the same composition as your actual material in the plant, for example. And a good thing is that in the last few years, there were a lot of CRMs that became available, not only from FLUXANA, but also from other sources. So you can rely on certified reference materials now. And if you do the calibration appropriately, you can even have like an LOI unknown calculated from your analysis as a res to 100. Yeah, that's about it about the casting powders. We're dead on 30 minutes, so I'm kind of proud of that. Thank you very much for your attention. As always, we'll look through the questions and we'll answer by email within the next few days, probably next week. And yeah, don't miss the next webinar, which will be correction models. I think it's the second part of my boss doing, like he did an opener with all the different methods, and now he goes into detail. I'm actually watching it myself, so I highly recommend it. And again, if there are questions, just send them to info@fluxana.com. Other than that, have a nice day. Thank you very much for the attention, and I'll see you next time then. Goodbye.